Hello friends, welcome to Risingpearl.com. This is series 13 where we're learning a great deal on surface areas and volumes. Friends, this is webisode number 15 and today we are going to focus on how do we solve questions on volumes of combination of solids. This is part 1. Now you should recall in the last 5 episodes we looked at how to solve questions on surface areas of combination of solids. So if you have not got a chance to take a look at it, I would suggest please take a look at those 5 episodes on Risingpearl.com where we looked at how to solve questions on surface areas of combination of solids. So now in this webisode, and we are calling it part 1, maybe we will take 2 or 3 parts to take a look at all different kinds of questions for volume of combination of solids. So let's dive straight in. Now, like we did for the last time about combination, when we were looking at how to find surface areas of combination of solids, we will devise a strategy, and our strategy will be a 3-step strategy. It will look something like this. Our first step will be we try and visualize in our mind which simple solid figures make up our given complex shape. So we will be given a complex solid and we have to find out the volume of that. So we will first try to break down the given complex figure or solid into simple solids. By simple solids we mean cuboids, cubes, cylinders, cones, spheres, hemispheres, and so on. That will be our first step. Second step will be find out which volumes we need to actually add and which volumes we may need to subtract to get the required volume which is being asked in the question. That will be our step 2. And finally, third and final step will be find the volumes of these individual solid figures or solids and calculate the required volume based on step 2. Now, as you can recall, we know how to calculate volume of cuboids, cubes, cylinders, cones, spheres, hemispheres, etc. from our earlier grades. We will use those formulas to calculate the volume of individual solids, right? And then we will use the step 2 to find out which volumes we should add and which volumes we should subtract, and using step 2 then we will calculate our required volume that is being asked in the question. Now let's put this theory to test and solve some real questions. So the question 1 goes like this. A solid is in the shape of, so the description of the solid goes something like this. So we have a cone which is standing on a hemisphere. So at this point you must be able to visualize that the solid is basically a cone which is sitting on top of a hemisphere. That makes up our solid. Now what is further given is that both of the radii are equal and they are equal to 1 centimeter, and the height of the cone is equal to its radius. Find the volume of the solid in terms of pi. So before we dive in, just this quickly, in terms of pi, it means that whatever is your final answer, it will be something like this. Some number, whole number or decimal or a fraction times pi, and all the units are centimeter. So this much centimeter cube. So the final answer will be something times pi multiplied by pi centimeter cube. So just wanted to highlight this. Now because there is no diagram which is given, let's use what is given in the question and draw the diagram for ourselves. So first we have a cone which is basically at the top, and then we have a hemisphere which is at the bottom. Now it is given in such a fashion that this radius, which is the radius of the base circle of the cone, is the same as the radius for the hemisphere. That means that our shape should look like this. That is, the radius of the hemisphere R, or which is R, is exactly the same as the radius of the cone. So the base of the cone and the top of the hemisphere, they exactly fit. That is what is given. So it is very important, friends, that you must be able to draw this solid in your mind very clearly. If you're not able to draw this solid, then you will have really a hard time solving this question. Again, let's just quickly recap. A solid is in the shape of, and the description begins from here, cone standing on hemisphere. So cone on the top. So we have a cone at the top. This is the cone, and we have a hemisphere which is at the bottom. So our solid actually has a cone at the top and hemisphere at the bottom. And it is such that both their radii is equal to 1 centimeter. So radius of the cone and the radius of the hemisphere, they are both equal, and the value is given as equal to 1 centimeter. Furthermore, which is given is that the height of the cone is equal to its radius. That means this height is also given. So if you were to imagine, so this is the height of the cone. So this height h is basically given as equal to 1 centimeter because the radius of the cone is 1 centimeter. So now we have to find out the volume of this solid. So what we should be able to recall is that volume of the solid will be really equal to volume of the cone plus volume of the hemisphere. So whenever we, like the way we were discussing about the surface area, whenever we talk about surface area, we think like how much, what is the area we should, paint. So similarly, whenever you think about volume, you can probably think about it as like, how much of water can you pour inside that, right? Because either it could be a water or it could be any kind of gas. It is easier to imagine it in terms of, water, right? So if I were to fill this entire thing with water, how much amount of water can I pour in? So obviously I have to fill this entire part with water, plus I have to fill this entire part with water. So the total amount of water that the solid can hold will be equal to the volume of the cone plus the volume of the hemisphere. So the volume of the solid will be equal to volume of the cone plus volume of the hemisphere. Now let's actually find out how we can solve this, right? So the volume of the cone, we know the formula for finding out volume of the cone is 1 by 3 pi r square h. This is the formula to calculate volume of the cone. So if this is r and this is our height, this is h. So the volume of a cone is 1 by 3 pi r square h, and keep in mind we have to find the answer in terms of pi. So we are not going to be really replacing the pi with 22 by 7 or 3.14. We will not do that. So it will be 1/3 pi, r is 1 square and height is 1. So 1 times 1 is 1. So it will be really pi by 3. This much centimeter cube. This is the volume of the cone, pi by 3 centimeter cube. Now let's take a look at what is the volume of a hemisphere. As you can recall, the volume of a hemisphere will be equal to, now volume, what is the volume of a sphere, right? Volume of a sphere is 4 by 3 pi r cube. So if this is the radius r, so for a sphere it is 4 by 3 pi r cube, but hemisphere is half, so it will be half times 4 by 3 pi r cube. So the volume of this hemisphere, which is the bottom part of the solid, will be 1 by 2 times 4 by 3 times pi, r is 1 cube, or this should be, this will cancel out. So it will be 2 by 3 pi, r is 1, 1 cube is 1. So it will be 2 pi by 3 centimeter cube. So 2 pi by 3 centimeter cube. Now if you were to now find out the volume of the solid, like we saw, which will be the volume of cone plus volume of hemisphere, right? It will be that. So the cone was pi by 3 and hemisphere was 2 pi by 3. So if you solve this, 3 is your denominator, pi plus 2 pi, which will be 3 pi by 3, 3 and 3 will cancel out, it will be equal to pi centimeter cube. So the volume of our solid, this entire solid will be pi centimeter cube. So friends, now one very quick observation I would like to make is that combination of solids, let's compare contrast between areas and volume. So if you have a combination of solids, what do we do when we focus on finding out the area of that versus what do we do when we find out the volume of that? So the first thing to keep in mind, this is very, very, very important. When calculating area of combination of solid, we do not always simply add the area of the parts that make up solid, because some of the parts of the area may disappear when we join the parts. So this is, let's call this very, very, very important to keep in mind. When calculating area of the combination of solid, we do not always simply add the area. We do not do that. We don't simply add the areas because some of the areas disappear when we join the parts. Now, what about the volume? Now, when calculating volume, on the other hand, of combination of solids, we always add the volumes of the parts that make up our solid. So this is very important to understand. When you are calculating the area, we don't always add, because some of the areas they disappear when you combine them. But when we calculate the volume, we always add the volumes of these individual solids that make up our final complex solid. It's very, very important to keep this in mind.